So you think ancient catapults are just dusty old relics of history? Well, think again. I mean, the very principles that let medieval engineers launch gigantic rocks hundreds of yards, turns out that's the same foundational physics that lets us put satellites into orbit. It's wild, right? Okay, let's really dive into this surprising connection. Okay, so how does this, a medieval siege engine, a machine made of just wood and rope, built for one thing, smashing castle walls, somehow become the direct ancestor of this? A modern rocket ready to literally break free from Earth's gravity? Well, the answer, and this is what we're going to explore, is a completely unbroken chain of physics that stretches all the way back, connecting these two things across 1,000 years. All right, so our story doesn't begin with rockets at all. It starts with the raw, brutal mechanical force of ancient siege weapons. And we're going to focus on one in particular, one that totally mastered the most fundamental force there is, gravity. Yeah, the trebuchet. You can basically think of it as a gravity engine. Seriously, by cranking up this massive counterweight, engineers were just storing up huge amounts of gravitational potential energy. And then when they let it go, all that stored energy converted into pure kinetic fury. That was its fuel. And the logic was simple. The bigger the counterweight, the more powerful the launch. But the real secret weapon, the thing that made the trebuchet so devastating, was the sling. It basically acted like a second stage on a rocket. See, as the main arm swung, it transferred all its rotational energy, that's its angular momentum, into the sling. And that sling would just whip around at the end at a mind-blowing speed, way faster than the arm itself could ever move. This is pretty much the mechanical granddaddy of rocket staging, right? One system handing off its energy to the next to get an even higher final speed. And don't forget, these machines were absolutely colossal. I mean, just take the Warwolf, built way back in 1304. Get this. It used a 1.5-ton counterweight to throw 150-kilogram boulders. That's like the weight of 2 full-grown adults. And it could chuck them over 200 meters. This was, without a doubt, the very first heavy-lift launch system in history. So why did the trebuchet become the king of the battlefield? Well, this chart here pretty much tells the whole story. You had other siege engines like the ballista that used twisted ropes. That's torsion for power. But here's the problem. Rope has a breaking point, right? You can only make it so big and twist it so tight before it snaps. The trebuchet, on the other hand, used gravity. And gravity, well, it doesn't really have a limit. You could always just pile more rocks into the counterweight box. Its only real limitation was the strength of the timber itself. So for throwing really, really heavy stuff, it was no contest. Okay, but raw power is kind of useless if you can't aim it, right? So the next huge leap forward came when mathematicians started to actually describe the path of that flying boulder. They were turning the art of aiming into a true science. And this was a revolution in thinking that unfolded over 2 incredible centuries. It starts in 1537 with Niccolò Tartaglia, who was the first guy to prove the ancient Greeks were totally wrong about how things fly. Then, about a century later, Galileo comes along and gives that flight path a precise mathematical shape. And finally, you have Leonhard Euler, who takes Galileo's perfect vacuum-sealed world and applies it to our messy one by figuring out how to account for stuff like air resistance. Before Tartaglia, pretty much everyone believed that projectiles flew in a straight line for a bit and then just fell straight down. He was the one who proved that's completely wrong. Gravity is always pulling on it, which means the path is always curved. And here's the real kicker. He was the one who calculated that a 45-degree launch angle gives you the maximum possible range. That is a fundamental rule we still use in ballistics today. And then came Galileo. He's the one who gave that curve a name and, more importantly, an equation. He proved that if you ignore air resistance, in a perfect vacuum, the path of any projectile is a flawless parabola. And this is it's a perfect example of the power of math. All of a sudden, the flight of a cannonball wasn't just a guess anymore. It was predictable. So, how'd he do it? This was his genius move. He split the problem in 2. He realized that a projectile's motion is really 2 separate things happening at once. You've got your horizontal motion, which is just a constant speed thanks to inertia, and you've got your vertical motion, which is constantly accelerating downwards because of gravity. By figuring those out separately and then just putting them back together, he could perfectly describe the whole arc. It was a completely revolutionary way to look at the problem. All right, let's jump to the next great leap, because you can see how this is all building on itself. We've got mechanical power down, we've figured out the geometry. Now it's time to introduce a new, way more powerful energy source: chemistry. But chemical rockets bring a completely new problem to the table. See, a trebuchet just needs one big push to get a rock over a wall. A rocket, though, it has to fight gravity every single second, all the way up to orbit. So the question becomes, how on earth do you calculate what that's going to take? So here's the core of the problem, the real tricky part. A rocket's mass isn't constant. It's burning tons of fuel every single second, so it's getting lighter and lighter as it goes up. Now, think back to Newton's second law, force equals mass times acceleration. If the force from your engine stays the same but your mass is going down, then your acceleration has to go up. The beautiful physics of Galileo and Newton, which worked perfectly for a cannonball that always weighs the same, just couldn't solve this new kind of problem. And the solution? Well, it came in 1903, and not from some famous university professor, but from a Russian school teacher named Konstantin Tsiolkovsky. He's the one who derived this equation, and I'm not exaggerating when I say this is the single most important formula in all of rocketry. This equation is literally the key that unlocked the door to space. So let's break this down real quick. Delta V, that little triangle V, that's your rocket's total performance budget. It's the total change in speed it can possibly achieve. And it really just depends on two big things: how fast your engine can throw exhaust out the back, and your mass ratio, basically how much of your rocket is fuel. And this is what leads to what rocket scientists call the tyranny of the rocket equation. Because of how the math works, getting just a tiny bit more performance, say you want to carry a slightly heavier satellite, it's not as simple as adding a little more fuel. Nope. You have to add more fuel to lift the new fuel, which means you need even more fuel to lift that fuel. It's this vicious cycle that means a tiny increase in payload can demand a gigantic increase in the size of your rocket. Okay, so to compare different rocket engines, engineers use a metric called specific impulse, or ISP for short. The easiest way to think about it is like miles per gallon for a rocket. The higher the number, which is weirdly measured in seconds, the more efficient that engine is. It's getting more bang for its buck from every drop of fuel. And you can really see that evolution right here on this chart. I mean, look at this. Early gunpowder rockets, super inefficient, around 80 seconds of ISP. Then you get to the V2's liquid fuel engine, and it more than doubles that to 210. Then fast forward to the space shuttle's main engines, and they double it again, getting all the way up to around 450 seconds. Each one of those steps was just a monumental leap in engineering. So, all of these different threads we've been following, the mechanical power from the trebuchet, the ballistic math from Galileo, the chemical propulsion from Tsiolkovsky, they finally all came together in one single, terrifying, and absolutely revolutionary machine, the V2 rocket. The V2 was truly a synthesis of everything that came before it. It was using the high-energy liquid fuels that Tsiolkovsky had only dreamed about. It had that hyper-efficient hourglass-shaped nozzle perfected by Robert Goddard that could shoot exhaust out at supersonic speeds. It was flying on trajectories calculated with Euler's advanced math. And then it added the final critical piece of the puzzle, a brain, a real active guidance system. I mean, its flight was like this perfectly choreographed dance of physics. First, it launches straight up. Then, internal gyroscopes tilt the rocket onto the exact angle pulled right from the firing tables, just like Tartaglia was doing for his cannons centuries before. Then, an accelerometer measures the speed and cuts the engine at the perfect moment. And from that point on, it's just a passenger, coasting along that same ballistic arc that Euler had mapped out on paper 200 years earlier. And that is the unbroken chain. From the trebuchet's simple mastery of a lever and a sling, to Galileo figuring out the perfect parabola, to Tsiolkovsky writing the equation that could handle its changing mass. Every single one of those steps was absolutely necessary. You just can't get to a modern rocket without passing through all of them, one by one. Which kind of leaves us with a really fascinating question, doesn't it? The laws of physics, gravity, motion, they haven't changed one bit since the Middle Ages. So as we look to the future, to crazy new ideas like electromagnetic launchers or even fusion drives, you have to wonder, what simple, ancient principle is just sitting there, waiting for us to rediscover it and use it to unlock our next great leap?